All right, this is section 1.3 in Math 100, quantitative reasoning. And what we're going to talk about today is just the types of modeling. So we're really not going to do specific problems and examples. That will be more in the next 4 sections, which will break down each type of modeling. But we kind of have built in a section just to describe the different types of modeling. So they are the types of modeling that we're going to cover are linear, quadratic, exponential, and logarithmic. Those are the 3 types of modeling. And they all are kind of patterned by different forms of equations, but they also are represented by different types of graph. Linear models typically have x to no power, just x to the first power. Quadratic models often will have the variable squared or x squared. Exponentials will either be an exponential function or the exponential function e to the x will feature those type functions. And logarithmic models, as you might guess, will either involve probably things that are log base 10 or a natural log. So how do we distinguish each type of modeling? Like I mentioned, that we're going to do it mostly by the graph. That we'll look at the graph and determine what kind of modeling it displays. So let's look at some examples. Linear models, starting out with linear, they have their graph is a straight line, as you can see in the picture. And that's just out of Maple that I cut and it was Maple that I generated the graph and cut and pasted. But I was able to find some, more specific examples. Like in science, you probably learned how to convert a temperature in Celsius to Fahrenheit. That formula F is 9/5 C plus 32. Notice the C does not have an exponent, it's just C to the first power or just C by itself. But you can see that the graph is definitely, if you plot a Fahrenheit temperature versus a Celsius temperature and continue to that, you definitely get a linear pattern. It is a straight line. So that's the first type of modeling is, again, linear. So going back to our list, the next type will be quadratic modeling. Quadratic models look more parabolic in shape. So here are some examples, like if a kid were to kick a soccer ball, the path of that soccer ball would be like an upside down parabola. So it would represent a quadratic model. Notice what I have written there, that projectile motion is a classic example of quadratic modeling. So both the boy kicking the soccer ball and the quarterback or the football player throwing a pass, the path of a football on a punt or a pass in football or a field goal, all 3 of them typically will be represented by this projectile motion or this upside down looking parabola path that they take. And that's kind of a summary of quadratic model. Again, we're looking for that parabolic shaped graph in for quadratic modeling. Okay, next, exponential models. Exponential models have, I describe it as a hockey stick shape, but they go up sharply, and it's not like quadratic where it has that U shape. It's more of a L shape or a hockey stick shape, if you can remember what a hockey stick looks like. So here's some examples of a classic example for exponential models is what they call exponential growth. And typically, if you look at the early period of the coronavirus or the COVID-19, these are very vivid. As you can see, this is from the UK. This is confirmed cases early on in the virus, often will produce a exponential shaped graph. Now, often if you look at a COVID graph, and actually, just about a month ago, if you look like at Texas and Florida, in fact, I put some of those in our homework, you are definitely going to see an exponential model. Now, later on, if you look at the whole picture, it may not be, when a curve starts to flatten, it flattens and it's going to take away that exponential shape. But if you take the early stages of a virus, it will often be exponential growth and have this exponential model look to it. Now, with a virus, if it takes off and there's nothing to contain it, it will be like that. And as you can see, that's kind of grim. But you got to remember, I'm not trying to scare anybody or get people panicked, but you got to remember with especially like a flu type virus, there's a lot of things that can slow it down. Containment and the social distancing, all that stuff we do will cause it to flatten. But also, when people get a flu, often there's some self-immunization that occurs too that will flatten it out too, because some people will naturally develop this immunity to it. Not everyone, but there's a lot of factors involved. So if you look at the whole scale long term, it's probably not going to look exponential. But early stages, definitely, of a virus that would produce this exponential model shape. Here's another example, population growth. I'm looking, I think this is world. I found this on the internet. I probably should be more careful what I post, but I would say that is probably a world population. Looking at it, it's in billions, because the population of the US is only around 340 million right now. As you can see, we're hovering around 7.5. So that sounds more like a world population figure as opposed to a single country figure. So there again, population growth can definitely be in this exponential form. We do models like, they joke about rabbits, but there's kind of some truth to that. If they multiply, they can grow really rapidly because they just reproduce very quickly. And if there's not other things to keep that population under control, again, you have this exponential growth. So kind of interesting stuff. The last thing is logarithmic, which has kind of an inverted hockey stick graph. And I didn't find particularly great examples for this. I just kind of cut and paste an example of a typical graph of natural log or log. I did see one actually of some examples of examples of flu strains that kind of flattened out, and even in some countries where the coronavirus has really been flattened, so to speak, the curve's been flattened, it starts to look like a logarithmic graph. So you're saying, well, how can you have both? Well, it's like I said, in early stages of some type of epidemic, you could have this exponential shape where it goes up sharply. But if that epidemic is contained long run, then its graph is probably going to look more like a logarithm because it flattens out. So it is kind of interesting to see that. So that's just a summary. Again, the hockey stick graph is logarithmic. The exponential growth is again this hockey stick shape. And then, of course, quadratic has this parabolic shape, and linear, of course, is straight line. And that really is it for the second. Just understand this graphical relationship, what it looks like. It's more a visual thing. We will, and the next 4 sections, we'll look at specifically how to work with quadratic models, how to work with linear models, etc. So that will be kind of what we'll do next moving forward. Today was this graph recognition. So if you can recognize the 4 types of graphs, that's really all you have to know for the homework. Okay, so that sums it up. We will continue on to section 1.4, where we will specifically look at linear modeling. And then the next section after that will be quadratic modeling. So thanks for listening in to my YouTube page and my Math 100 students. hopefully you will enjoy the rest of your day. Thank you.